question is, have you got a definition of cerussite versus muscovite?
Nice. It's like a setup, because that's one of my pet peeves. So, cerussite is a field term for very fine-grained muscovite, and you need a petrographic analysis to be able to determine that.
Do you want to come over this way so we can closer?
Okay. So, cerussite's a field term for very fine-grained white mica, and sometimes the crystallinity of the white mica can tell you if it's cerussite or not. You'll have a very narrow, very sharp absorption feature at 2200 nanometers. That can be cerussitic, but you need confirmation from something that's actually measuring the grain size.
Yeah, the reason I'm going there is because I see the cerussite as an alteration product from chlorite or whatever via the illite. It goes through illite, measurable in XRD, then to cerussite.
Yep, smectite, illite, muscovite, cerussite. That's the sort of sequence of a thermal gradient and the mineralogy as it changes along the thermal gradient.
Yeah, it's in the alteration packages.
In the...
It's in the hydrothermal
yes.
alteration.
Yes. Yeah. Did anyone want to add anything to that?
No.
Okay. But, you know, people jump in and say everything's cerussite wherever they see a white mica spectrum, and it's not the case. It could be primary white mica, you know, and you've got to be able to determine if it's alteration related or metamorphic related. You have to be a geologist and put on your geologist hat and understand the occurrence of the minerals in the context that they're occurring in.
Hello. I'm just wondering about the integration of old data sets and new data sets when it comes to SWIR. So stuff that was collected, say, by PIMA 20 years ago, how easily can that be integrated with things that are collected now? Because I don't think a lot of QA/QC was done back in the day. And so is it better to just, you know, bring it all in again, reprocess it through ICIRIS or something like that, or can they be compared?
I think as far as mineralogy goes, it can be reprocessed and you can actually get the comparable mineral information. The only things that might be a little different is that comparing the PIMA from a TerraSpec is that the wavelengths might be slightly different, so you're not going to be able to compare the wavelengths of the white micas or other minerals directly with more recent readings, because the PIMA had sometimes between PIMAs there might have been like 4 nanometers, even sometimes 6 nanometer shifts even between the equipment. So you had to be really careful about the instrument that you use. So those are the kind of things that you may not be able to compare. But if you boil it all down just to mineralogy and mineral variations, you could still compare that information, yeah.
And so nowadays, all the different instruments that exist, those are relatively comparable when it comes to wavelengths?
Yeah. Nowadays there's a lot more, things are much more robust. Yeah. So the TerraSpecs and again, within a particular project, I would recommend that you work with a small number of spectrometers as possible, and certainly the same variety. So like those guys that,
if you can, just one.
Yeah. So those guys are like doing their optrics. So wouldn't want to then bring a TerraSpec in and then compare those results, because there's, between different spectrometers there are slight variations. So you just got to maintain that consistency. Oh yeah, actually, Tony might have something to say with that.
I can comment from personal experience, having that wavelength shift. So I've dealt with an exploration project that had TerraSpec data collected on it, and the project geologist actually made a comment that the classification that was applied to the white mica composition didn't look quite right, and so I went back and actually, so nowadays you can get wavelength calibration standards that you should be scanning at the same time you're collecting your data as you do with other analytical instruments. So just to make sure that your instrument is properly calibrated. So in that particular situation, the spectrometer was 4 nanometers out, so
Wow.
basically had to send it back to the workshop to get it
Yeah.
Recalibrated.
Yeah.
recalibrated, send it back to the States in that
Yeah.
instance. So yeah, just to
Excellent.
be very wary of that. So you can just get the standard directly from the supplier of the spectrometer. So
Yep, yep.
just email.
Yeah, it's good even just to set up your own standards within your project as well. and things
Well,
like
yeah,
that.
that's
Yeah,
right.
yeah,
So
absolutely.
we went from sort of, just actual sort of pure sort of mineral standards to just a sort of more of an international sort of recognised sort of standard, just a sort of a sheet of mylar.
Yeah.
Well, one thing we encourage people when, if you're using the Sirius system, when you're importing spectra, we have fields in there in our metadata input where you can actually put what spectrometer was used for that spectrum. So that allows you to track. So, yeah, and those can be historical spectra. So there's things that we didn't used to do historically. It's really important to actually track that information and put it into your databases. So if you start to see these sorts of variations, where you might have like one part of the project area might have very distinctly different wavelengths from another, it could actually just be the spectrometer. Yeah. But anyway, good question.
And just in relation to recalibrating the instruments, you can get it done in Australia with portable analytical systems, yeah.
Yeah, now this is going back. Yeah.
Oh, well. You can also, if you do have historical data that is out by 2 nanometers, say, you can programmatically correct for it, but it's not straightforward. Yeah.
I've got a question for Sasha. Around the machine learning approach with the ASIRIS, you've got 1 million spectra or something you're working with. How have you been able to add data to that from the industry stuff that you're actually measuring? So build the power of the machine learning models.
Oh, yeah, the whole.
The industry sort of gone about that approach, like sharing their data for the better good.
Well, it's all completely sterilised. There's absolutely no location data, so all we have is just the sample and the mineral result. So we've actually used real world project spectra in the system. So
Really building that.
absolutely, yeah.
Is it validated?
Well, it's validated by full interpretation with the spectral expert. So we've not actually done any XRD or anything on those samples, if that's what you mean by validation. But that is the next step for us, just to create a validated step. But the customers themselves are actually doing their own validation as well. So we've had feedback that we're getting some really good, the mineralogy that we're reporting matches really well to validation by geochemistry and validation by XRD as well. So we've not actually done the validation, but the users have. Yeah.
Okay, couple more questions.
Can I just make a comment? One of the great things about hyperspectral data gathering is you gather buckets of data, huge amounts of bloody data. You need 2 engine aircraft just to fly the computer with a high map. But the big problem is that when you produce those orgasmograms, you've just got too much noise. Our surveys that we did, we used a simple model. And so we're looking for mineral destruction through alteration to mineral products, and trimmed it down to about 3 or 4 minerals. And all of a sudden you get a very special output. We found a new one in Morocco called Misanite. When we ground truthed it with a portable spectrometer, it was actually mica and carbonate. So it was the M3, or the carbonate alteration regional, over 30k by 12k area. And within it you can then see the other alteration patterns.
Yeah.
But that model is the most important thing.
One more question over there, then we'll better call it quits for this session.
Sorry, this might be quite a simple one. Just wondering how much one of the speakers indicated that your infrared signal was degraded with pulverising the sample. I'm just wondering how much, and is that, can you counteract that? Can you see through that degrading?
I actually have a slide that I hid because I had to chop out slides. Can I show that to answer the question?
See, what happens is that, just while Melissa's finding that, the finer the grain size, the more reflection you get off the surface of the sample. So so the less penetration. So basically the features become smaller and weaker, but the brightness increases. So you just get features that are closer to the noise, really, so with the really fine powders.
I'm just looking at it from the perspective, we've got quite a library of sample pulps.
Yeah.
We don't have so much core.
Yeah, so sometimes pulps are the only things that you have, and you can still get a lot of information.
Yeah. We actually did a test about many years ago when I was still working with Genesis for that very reason, to see if it could actually fit into a standard lab flow process where most things are done on pulps. And so we did a large test. We took core material and then we crushed it to various sizes, dried it and looked at various variations. Certainly, as Sasha was saying, you do get a degraded signal. You just get too much reflectance. However, you still can see the dominant features. So if that's all you've got, I suggest it's worthwhile trying. It's not the optimum material that you'd go for if you're able to start from scratch, but you still can see the main features. Melissa?
Okay, this is from a paper by Dewey et al. 2017. Basically, the smaller particle size generates high reflectance values but weaker features. And they conducted an experiment and they had 4 different rock types: silica breccia, sandstone, granite, serpentinized harzburgite. These are the abbreviations here. And they had 5 different levels of cutting done to the samples. The first one was just drilled, the second one was slabbed, so just cut straight with a diamond saw. Then they polished it down to 6 micron, polished it down to 0.25 micron, and then a -80 mesh for a powdered sample. And they've stacked it up. Here's the colour code. Black is the drilled sample, red's the cut, green's the 6 micron, dark blue's 0.25 micron, and light blue is the powder. And just for, say, the silica breccia up here, you can see the size difference between the absorption features. It's quite shallow when it's a powder compared to when it's just the slabbed core. Similar for the granite, and it's these absorption features around, say, when you're looking at illite 2200 feature, it's really quite shallow for the powder compared to just the drilled or the cut surface. So that demonstrates that when you crush a sample, turn it into a powder, it has greater scattering of the light amongst the small particle size, and so there's less energy being reflected and captured by the spectrometer's detectors. That's the reason that you get shallower features. Does that make sense?
Yeah, no.
We are running over time, so I'll just get you all to thank our speakers in this morning's session.